Good afternoon, everyone.
Good morning.
So on this one, we're going to look at Newton's law of cooling. Well, we're going to look at differential equations, actually.
Yeah.
Not to be confused with differentiation, which is what we've been doing for weeks.
Yeah.
So it's basically, don't confuse the shun with the al. As we say, differentiation, even though it's not spelled that way, comes from the French, not the Latin. And this is Newton's law of cooling, or this is the starting point. This is like the model of it, the model. And what we're going to do is we're going to get to a stage where we've got the mathematical solution. So where it comes from is this method of using calculus. It's to do with, remember this, when we have this. What was the derivative of that when we had y equals e to the x? So that, for example. What was the derivative of that?
The x2, y equals x2.
No, there's no 2 there. Yeah. Making it more complicated than it is. Yeah, just e to the x.
Oh yes.
Yeah. So basically what that's saying is the answer to the function is the same as its gradient. So if you plotted it like that, the gradient at any point would be identical to the y answer to the question. Okay, so the gradient's the same, and it comes out of natural laws. It's quite a useful part of nature. So this principle we're going to do is applied to these kind of situations, and there's loads of examples. But the common ones, you might know this one. I know you're not electrical guys, but you might know this one. So the volts across a capacitor. Have you seen this one? In fact, you have seen this one because it's on one of the assignments. So that's not a plus, it's a minus. So you remember that one? Yeah? And then another one you might know, might not know, is this one. It's the right way around, minus lambda t. So this is a radioactive decay, so that's your half-life, that lambda. So if you played that game, half-life, that's the symbol you use, isn't it, on the game? Half-life, lambda, Greek letter lambda. Another one, probably, I'll come to that one in a minute, y equals y to the 0. So this is to do with population growth, i.e. us, but it can also be something less nice like bacteria. Okay, so it follows this formula where you've got some multiplier here, k, some constant. So some populations grow quicker. So there, you could say it's like their half-life as well, but it's their double life. So the double life figure. So obviously rabbits breed quicker than human beings, allegedly. And another one, you guys might know this one, the tension on a belt. Have you seen this one? So e to mu theta. Okay, so that's the tension on a belt. That's your angle of lap where the belt touches the pulley. Okay, and there you've got some constant out front. So they're all typical examples, and we're going to come up with one from Newton's. So what this is a first order differential equation. You get them to many different orders, but they get more and more complicated, obviously. If you get some notes out, say you get Ken Shroud's book or whatever, and you're looking at differential equations, the one we're starting with is basically the 101, the cos 101, the first sort of example they do, the basic ones, and then they get more and more and more complicated as you go, as the orders get higher. So the method is this. So you'll be given this, and you've got to basically derive the mathematical equation from this, the solution. The T's are to do with temperature. The big uppercase T is temperature, and the lowercase t, no surprise, is time. This TA is to do with the ambient temperature, so what it is in the ambient in the room, and this is to do with the temperature of the material. So for example, if I had a block of aluminium, 4-inch square, 100 millimetres, 10 centimetres, whatever you want to use, and I put that in this room, it's quite warm in here today, so let's say it's 20, could be 23 degrees. Okay, and this says it's 100 degrees. Obviously it's going to start cooling down. The temperature goes from the hot to the cold. So it's going to travel, and this K here is going to decide how fast it changes. So this is an expression that Newton came up with. So the change in temperature depends on the time. Okay, so it started there. Then he did this process we're going to do, and he comes up with an expression that's similar to those we've just seen. Okay, so it's not difficult, this bit. So, what do you think would make this K different? What would make it change? What would make it bigger or smaller? That's to do with these values. So it's to do with what would affect the rate of change.
The size.
No, it's not referring to that. It's surface area, yes.
Yeah.
Okay, so a bigger surface area, so if you can make the shape.
Yeah, that's not
So it's got a bigger surface area. The
material.
material, yeah. So for example, wood is going to have a different K to say water. Water's a good conductor. I'm not actually sure what it's like as a radiator of heat actually, because it's more to do with radiation of heat. But probably, so I'm not so sure how it compares that way. But obviously, wood's not going to be as good a radiator of heat as say aluminium or metals. Okay, plastics, wood, these things are going to be less of a radiator. You would think, you've got to be careful though on what conclusions you come to, because quite often the facts are different. And you see that in life in general, don't you? Anyway, so it's going to be affected by the material. So it's that rate, and to get that value, you've got to get some information, some initial values. But we'll see when we get there. So let's have a look. So the first step we're going to do is we've got to rearrange this. I did say that this differential function is a bit cleverer than it looks. You can actually start to split it up, and that's what we're going to do. So we're going to split it like this. So on the left-hand side, I'm going to take this to this side, to the left-hand side, and I'm going to take this dt to the right-hand side. So that will give me this 1 over t minus ta dt, capital T, equals k dt lowercase t for time. Is there a minus sign in there that I missed out? Yes, sorry, I missed a minus sign here. Okay, because it's going down. As it cools, the temperature's going to drop. So the whole process is going to be lower. Right, and then I can do an integration of both sides now that I've got these dt's. So like this, that should be a 1. Whoops, missed something. dt. Okay? I'm going to move along. So, anybody know off the top of the head what the integration of 1 over t minus ta? I did hint at it in a previous lesson.
Log.
Log, yeah, very good. Well remembered, yeah. So this is going to be log of this value. Natural logs, remember. So it's going to be log of t minus ta will e plus c, but I'm not going to put it in yet, we'll come back to that. And then that'll be equal, so this one, so what's this one going to be? Minus k. It's not got a variable, but it's an integration.
Minus kt plus.
Yeah, it's going to gain one, yeah. So minus kt plus c, because it's not a definite integration, it's an indefinite. So we always end up with a c constant. Now the question for you is, why have I only got it on one side? What about this side? Okay. Anybody? Well, there is one on this side, but it's some unknown. C is an unknown value, which could be 0, could be a big number, small number, negative number, we don't know. What I've done with this one is I've taken it from this side and added it to this one, or subtracted it maybe. We don't know because we don't know what sign it is. We don't know anything about it. So I've added it to this side. Might as well only have one of them as two of them. It's going to make it simpler. Okay, so now we don't like this, so what's the way to get rid of a log, natural log? How do we get rid of any function?
Log to the base of cancel it. The opposite of
The opposite, yeah, we do opposite, so it cancels out. So we're going to raise it to the it's a natural log, so it's going to be this base e that I mentioned earlier,
Log to the base
Euler's number. So we're going to get t minus ta will equal e to the minus kt plus c. Okay? Agree with me? Now this is just a indice, laws of indices. So you know this when you say you've got x to the 2 like this, x to the 2 times x to the 3, we just add the powers together. Well, that's the same, but we're working backwards. If I work backwards, I'm going to get this. Okay? So, I can rewrite this like this. Not like that. E to the c. Okay? Now this here is exponentially Euler's number to some value that we don't know what it is. So it's some number which we don't know what it is. Well, I might as well just change the whole thing to some number that we don't know what it is, because that's what it is. It's 2.718 to some value. It's going to give us some value we don't know what it is, because we don't know what c is. So I might as well just rewrite this like this. I'm going to make e to the c equal to, I'm going to label it like this, the c original. Oh, that'll make a bit more sense later, hopefully. So if I bring that to the front, I've got this now. Okay? So that's like, so earlier, the start of the equations. So we've got something we can use now. What we don't know though is we don't know what our values are for CO and this minus K. We can work out though, we can work this out though. So if I make, at time 0, what's going to happen to this formula at time 0? So I've got my block of aluminium and I plonk it on the desk. In that instant in time, what would, which is t to 0 basically, what would this formula look like?
T minus TA minus T
Yeah.
plus CO.
Let's have a look at that. Good one. So this would equal that. Why would it? Because that's 0, and what's anything to the power 0?
1 itself.
Yeah, 1. So I've got this times 1. So what we're saying is that equals that. Okay? That's what we're saying. So what we're saying in effect is at time 0, this is equivalent to our ambient temperature and our starting temperature, say about a block of material. There's that difference there. So I've now got my final formula. You don't know what K is, but K is dependent on the material. So that one we've got to work out at the time by doing a bit of research, doing some a bit of experimenting and see what we get. So what this really is saying is that this is going to be our value after some time. So this t value is going to be a value, so say after 5 seconds or 10 seconds or 10 years, it's going to give us some value, and this is going to be our original condition. Okay, so from this we can start to do something. So let me make sure you've got that down, because I'm going to do an example, but I need to make some space. So I'm going to put the formula over here. Like that, yeah. Am I okay to rub everything off?
Yeah.
Anybody say no?
Yes, yes.
Everybody say yes. And all this as well?
Yeah.
Okay. So an example and how we find this value k. So we've got this example. We've got a chef who makes a pan of pasta sauce and uses half straight away and then freezes the other half for the later use. The half to be frozen needs to cool to 25 degrees C. The room temperature is 20 degrees C. So he's got to cool it down to 25 degrees C before placing it in the freezer. The original temperature of the sauce was 90 degrees. Yeah.
What question is this on the sign?
It's similar to which one is it? Question 7. Question 7. Yeah. So it's a bit slightly different. Your example. It's not as nice as pasta sauce, but it's a similar idea. So we've got an initial condition. So the ambience is 20 degrees. The required temperature that we want is when we require, what shall I call this? I'll just call it R for required, not very imaginative. And that is 25 degrees. And the actual temperature of the pasta sauce is 90 degrees. It's fairly warm. The sauce was placed in a sealed container and left to cool. It was found to have cooled to 80 degrees C in 5 minutes. So when we get to T5, it equals 80 degrees. So how long does it take to cool to 25 degrees? That's 5 minutes, by the way, not seconds, minutes. It's not that quick at cooling. So from that initial condition, you can see what we're going to get. We can work a value out for k because it's going to tell us some information about it. Okay. So this chef, for example, is at the end of the day. He's got some time. He does a bit of cleaning up, and then he wants to go home. He wants to know how long it's going to take before this will get down to cold enough temperature so he can stick it in the freezer. You know how it is. You can't just stick things in the freezer when they're fully hot. It's not good for your freezer. It starts warming up the rest of the food and can damage it, corrupt it.
It's not good for the food as well.
Exactly, yeah, no good for the food. Exactly. We don't want that. We don't want to waste our food. Especially if it's
You
good.
always let it cool down, then you put it in the fridge or freezer.
Yeah. That is perfectly it. I mean, obviously, if he realises it just sat there on the side, it's going to take too long, he can. It's a clever chef, by the way. If he realises it's going to take too long, he can run it under the tap, maybe. Something like that to speed up the process while he's doing his cleaning down for the night. So let's see what he does. So we know this now, or we know that amount of information. TA is 20. Let's see how they fit into the formula. So we've got this. We've got at 5 minutes it cooled down to 80. And the initial, the ambient is 20. So it's that formula. Let me put the formula in first. So we've got T minus TA equals CO e to the minus KT. So T is our cool temperature. This stuff on the left is basically the result of time. What's happened to the material after time has acted on it. Well, this CO stands for C original. So what was it originally? Where it's come from. So we've got here 80 minus 20 equals. So this is 90 starting point minus the ambience. So the difference between the two. E to the minus KT. And T is 5. So let me put that in. So what is K? Once we've got that, then we can work out what temperature it will be at any moment in time.
Why did you do 80 minus 20?
Right, this represents the left-hand side of the formula, the equation. It represents what temperature it is after the time's had its effect. So this is when, this basically I could write in here, for example, that would be another way of expressing it. So it's saying what was it after 5 minutes? It's gone down to 80. So this is what I've been able to measure. So the chef's been able to measure this. He's put his thermometer in it, or he's got one of them infrared guns, and he's able to say, right, it's gone down to 80 and I've been waiting 5 minutes. So how long is it going to take to get down to 25 degrees? That's what he wants to know. And then he knows if he needs to give it extra cooling, or he's going to have a late night. Okay, or if he doesn't have to worry, he can just get on with his cleaning. Because you know it takes a bit of time to clean and it's got to be done, got to clean everything down. So let's have a look. So another way of putting this obviously is 60 equals 70 e to the minus k 5, or minus 5k might be nicer. So that means I can start doing some rearranging. So I've now got 60 divided by 70 equals e to the, I'm going to bring the 5 to the front. So what would I do next? I want to get rid of this, get it out of this function really. I'm trying to make k the subject. So what am I going to do with this? How do I get anything out of a function? Like we said earlier.
Root it.
Yeah, do the opposite basically. The opposite function to Euler's number is natural logs.
So log
Okay.
is 10.
So I'm going to do natural logs of both sides. 6 over 7, because it cancels down. And that will make it equal to minus 5k. So all I've got to do is put that in my calculator, divide by 5, and we'll get the answer to k. Now we've got to be careful here, because when I do, well, we've got to think about it. When I do my log of this, log of 6 to the 7, that's less than 1 actually, so I'm actually going to get a negative answer. Anything less than 1 gives you a negative answer for your y value. If you plot it, it looks like this. And that there is 1, so any value less than 1 of x gives you a negative answer. So that's useful to remember. And remember, it never gets to 0, so 0 is forbidden in logs. All logs look the same shape, whatever it is. So I know this is going to be minus 1, so that's minus, that's quite handy. So it's going to give me a positive value for k. That's quite useful and relevant. So let's have a look. So log, so it's going to be, you can get this in here, 0.01542. 1542 equals, that's a negative. So if I divide by that, obviously it's going to become positive. Or I can just have multiplied through by minus 1 and make it all positive anyway. It's the same difference. So if I just go over here, I've now got, that will give me, I'm finding my place. So therefore k equals 0.1542 divided by 5 equals 0.031 per minute. I'll put there. Not sure about that, but okay. 0.031. So that's my k. So that means I've now got a formula. So I've now got the formula of this. T minus TA equals CO E minus 0.031 T, where T obviously be time. So that means I can now work out how long it'll take to get down to 25 degrees. So if I substitute this in, going back to my formula, so I've now got on my left hand side 25 minus 20 will equal 70. That's my starting difference. E minus 0.03 T. Which obviously is 5 equals 70. E minus 0.03 T. So same, exactly the same as what we've just done. So if I divide 5 by 70, it's going to equal, that will equal E minus 0.03 T. Then take logs of both sides, natural logs of both sides. So I'll then have natural logs 5 over 70 equals 0.03t. So I find the answer to this, divide by that, that'll give me t. That's how long it takes. That gives me, if I do that, I get this, t equals 85.13 minutes. So if it takes a long time to clean, if he's got a lot of work to do, maybe sorting all the eating area out or something, then it's okay. But if he wants to get off in half an hour to catch his last bus or whatever, then he's obviously going to have to do something. He's going to have to put it under the cold water running tap. Okay. So that's it. So if I plotted that, well, what would you expect? It took, in 5 minutes, it dropped 10 degrees. And yet to get down to 25 degrees, it takes a long time. So if I plotted it, what kind of shape would you expect?
Curve.
Yeah, I mean, what sort of shape? You got, let me have a guess. Well, it's, if I've got temperature here and time here, so we're starting up here at 90 degrees.
Yeah, it'll be like this.
Yeah, is it going to go down steep and then?
No, it's going to be
it's going to go down steep and then...
It's going to go in a constant thing, it's not going to just go.
Is it all constant? Is it
No,
like
it's
straight
going to
line?
be constant,
It has to
down,
go
down, steep a lot first,
Yeah.
and then slowly.
Yeah, perfect. Yeah, it can't be a straight line because it's not linear.
Yeah,
Because it's changing a lot to begin with and then slowing down. So it goes something like this.
Yeah, and then gradually touches.
And it, well, probably mathematically it never touch it, but in actual fact it
Yeah,
probably
looking
will.
at it, it seems like it touches.
Yeah, it certainly get harder and harder for it to get down to 20 degrees of the room. As it got near, when it got to 21, it'd be really hard. So it's going to. So you've got basically, if this is 90, let's say this is about 80 here. So to get down to 20 down here, well, 25 is a target there. 20 is a target. To get down to 25, what would that be? 40, 20. No, that doesn't make sense. 60 difference. 50, losing track of it here. Somewhere around here. I'll meet defeat at that point. So to get it down a bit lower, actually, down here, 25. That time is 85 minutes. There. So the rate of change is quick to start with, which is what the formula says. And then it's going to, because if you rearrange it, you're taking it away from your starting point. This one, this equation, like your standard, like the charging capacitor one, where you've got to take it away from 1. Same with this one, so you're taking it away from 1 basically. So it's going to slow down, and it's going to get really slow. So really, to get it down to the ambience in a rush, you'd have to really put it under, you'd have to put it with water that's actually maybe cooler than the room to make a big difference. The bigger the difference, the quicker it changes. So his best option is to actually put it in iced water maybe. Get some ice out of the fridge, out of the freezer. Put it in some water in that and it'll cook. That's going to make it cool quicker because it's going down below the 25. Because when you start to get near your ambient temperature, 20, it's not going to move very fast. And if you run tap water, depends what time of the year it is, but it can easily be 20 degrees at certain times of the year in the summer. So in the winter you might get away with it, but it's best to get some ice out of the fridge. Okay? So you okay with that? Straightforward?